Today, we're going to pull back the curtain on the invisible war that happens inside our bodies. We're looking at how antiviral drugs pull off one of the cleverest tricks in medicine, sabotaging a virus.
So let's start with this really fascinating question, right? How do you fight something that isn't even alive? I mean, with bacteria, you can kill them. But viruses, they're in this weird gray zone. They're not technically living, which means our entire strategy for fighting them has to be totally different.
And here's the key takeaway. A virus is totally useless on its own. It's just a little piece of genetic code in a protein shell. It can't do a thing until it gets inside a living cell. So it's less like a creature and more like a microscopic pirate looking for a ship to commandeer.
And, once these hijackers get on board one of our cells, they have one single, relentless goal in mind.
Just think about that for a second. Your own cells, the very things working to keep you alive, get their job description completely rewritten. The virus takes over the controls and forces that cell to forget its normal duties and just start churning out thousands, sometimes millions, of new copies of the virus.
And this whole takeover, it's not a chaotic mess. Oh no, viruses are incredibly systematic. They follow a very specific step-by-step playbook to get what they want.
It's basically a 6-stage heist. First, the virus has to attach itself to the outside of a cell. Then it's got to find a way inside. That's entry. Once it's in, it sheds its disguise, its outer coat, to release its genetic instructions. Then comes the main event, replication, where it uses our cell's own machinery to make all the new virus parts. After that, it's just assembly, and finally, the great escape, releasing all the new viruses to go infect more cells.
Okay, so if that's the virus's game plan, how in the world do we stop it? This is where the real genius of antiviral medicine comes into play. And the goal? Well, it's probably not what you think.
You see, since a virus isn't really alive, you can't actually kill it. So instead of destruction, the strategy is sabotage. Antiviral drugs are like little wrenches thrown into the gears of that virus-making factory. The whole idea is to interrupt that 6-step process at a really critical point and stop the virus from ever making copies of itself.
So think of this as our battle map. It shows that 6-step cycle, and each one of those stages is a potential vulnerability, a weak spot where a drug can step in. Some drugs are designed to block the virus from ever getting in. Others stop it from uncoating. But a lot of them target that supercritical replication step, the part where all the new viral pieces are being made.
All right, let's get concrete and see how this actually works. We're going to look at 2 really brilliant examples of this sabotage strategy in action.
So our first strategy targets step 4, replication. Imagine the virus using your cell as a giant photocopier to print out its genetic blueprints. Well, this plan is all about feeding that photocopier faulty paper that just jams the whole machine.
Acyclovir is a perfect example. It's a common drug used for herpes viruses. It's what's called a guanosine analog, which is just a fancy way of saying it's a fake version of one of the building blocks of DNA. And the really clever part is, the virus-infected cell is working so fast that it accidentally grabs this fake piece and tries to use it to build new viral DNA.
And this is where the trap springs. The fake building block gets added to the growing DNA chain, but it's a dead end. Nothing can be added after it. The whole process just stops. It's called chain termination, and it brings that viral photocopier to a screeching halt. No more copies. Game over for that line of replication.
So if Plan A is all about stopping production, Plan B is about containment. This strategy focuses on that very last step, release. Basically, it lets the virus make its new copies, but it makes sure they can never, ever escape to infect other cells.
Take the flu virus. It has these spikes on its surface called Neuraminidase. After all the new virus copies are built inside the cell, they use these spikes like tiny molecular scissors to snip themselves free. That's how they escape and go on to the next target.
Well, drugs like Tamiflu are designed to jam those scissors. They're called Neuraminidase inhibitors. They bind to those spikes and just make them useless. So the new viruses are fully assembled, they're ready to go, but they're trapped. They're stuck to the outside of the cell they just came from, completely unable to spread the infection.
Now, these sabotage plans are incredibly clever, but the story doesn't end here, not by a long shot. The truth is, we are in a constant, never-ending arms race with viruses.
This quote from the research really says it all. For any drug we come up with, we just have to assume that eventually, viruses will figure out a way to get around it. It's not a possibility, it's an absolute certainty. And here's why.
It all comes down to a numbers game. Viruses replicate at an incredible speed, making billions and billions of copies. And their copying process? It's really sloppy. There are tons of errors or mutations. Now, most of these mutations are useless, but every once in a while, a random mistake might just slightly change the shape of an enzyme or one of those neuraminidase spikes, just enough so our drug doesn't work anymore. And then, that one resistant virus is the one that survives and takes over.
Which kind of leaves us with this final big thought. This is a battle of constant innovation. As viruses adapt and evolve to get around our best tricks, scientists are already working on the next wave of sabotage plans, targeting different steps, using brand new mechanisms. So the question for all of us is, what will that next generation of antiviral sabotage look like? And how will we stay one step ahead in this microscopic war?